Okay, so for this problem, what we've got, okay, there's my pen. We've got the ideas we talked about yesterday, mutually exclusive and independent. Mutually exclusive means that both events can't happen at the same time. Independent means the one event happening does not affect the probability of the other event happening. Okay, and we're going to come back to these ideas again, but we are going to get more into kind of probability calculations using the addition and multiplication rule today. But let's kind of see which one of these is true. So maybe the easiest way to think about this is remembering one of the rules about independence. And what independence means is that, like I just said, the probability of one event does not change the probability of another event happening, which means mathematically, oops, I'm doing this wrong, the probability of A and B happening is just going to be the probability of A times sorry about that, I lost my pen, probability of A times the probability of B. So if I just remember that from yesterday, probability of A and B has to equal the probability of A times the probability of B if they are independent. And therefore, if I multiply 0.48 and 0.4 as my A and B, now it doesn't really matter what we get there. I think it's going to be 0.192. But whatever we get there does not matter because together, A and B, we already know its probability of 0. So if I'm right, I think 0 equals 0.192 or whatever that happens to be. I didn't really do the math there. Because these are not equal, we can say, okay, they are not independent. So we know they're not independent. So anything that says that they are independent, we can cross out. So B and C we can cross out. Now, we did have a couple of ways of thinking about mutually exclusive. One was that P, the probability of A or B equals the probability of A plus the probability of B. Now, that's all well and good, except we don't know the probability of A or B. We can't use that. Another thing we know is that the probability of A and B, if they are mutually exclusive, is 0. Okay, and that's what we have here. The probability of A and B is 0. So they are mutually exclusive. The answer here is A. They are mutually exclusive, but not independent. So there we go. That's the case. All right. Hopefully that's clear enough. Any questions on that? So we're going to do a little bit of an activity to start the day off. And what I want you guys to do, if we don't get everyone to get through this completely, that's okay. But we're going to do play some trash ball. So first of all, I need a regulation wastebasket. So I've got one right here. And you need to have a regulation wadded up piece of paper. And I want you to take 10 shots and see how many you can make. And I want you to go through the 2 trials of this. So 20 total shots, but kind of keep track of each one. I'm having you do this twice so we can get more data points. But anyways, 2 trials. If you only get through one of them, that's fine. So shoot 10 times, how many did you make? Shoot another 10 times, how many did you make? And go for it. When you're done, you can add your dots onto this. We're going to make a dot plot of our results. So, I mean, I got 26 trials, but some of these I wasn't sure about. So it could be up to 30 potentially. So whatever number you're satisfied with, of course, we probably want to make sure that we use a pretty standard dot when we're making dot plots. But anyways, I got 26. I'll go with that number. I don't know if you guys counted something different when you counted through. But out of 26 trials, we want to figure out the probability that someone's going to make 6 baskets.
And this is not, mind-blowing stuff happening right here. We're just gonna go here. So what is the probability of someone in this class making 6 baskets?
Would it be 3 out of 26?
That's it. That's all there is to it. So you go to the 6, there's 3 observations, and that's what we've got. So pretty straightforward. Now everything is the same. I just changed the question slightly. It says, what's the probability of someone making more than 6 baskets? So what do we do for this one?
Add all the data points that are more than 6.
Okay. So these are all my data points that are more than 6. And let's see, we've got 8. See, 8 out of 26. I just want to do a quick comparison, because you guys are super competitive, I know. Oh, this is really close. So you guys got 8 out of 26. My 5th hour, they had 10 out of 34. So when you look at it, you beat them by 1 percentage point. You're 1% more likely to make a basket, 7 or more, I should say. Congratulations. All right, 8 out of 26. Nothing super fancy going on. And the probability of someone making an even number of baskets.
Twelve out of 26.
Okay, I got 11, but that might just be we're counting different dots. So I got 2 right here, 1. I got 3 there.
I got
3
11
there,
too.
and 2 there. So yeah, I mean, some of it just depends on what you're counting as a data point here. But I guess whatever that added up, 11 out of 26. 0, I believe, technically is not an even number, though I don't 100% recall off the top of my head. So anyways, all right, this is empirical probability. There are questions that might show up like this on, it could be an FRQ, it could be a multiple choice, but you kind of get the idea. Nothing really super fancy about it or super complex, but it's worth seeing it and get to show off your mad hooping skills, or in my case, lack thereof. All right, so let's look at this. We've got histogram. Okay, and this histogram is actually giving us numbers. I don't want to take the time to go through these problems, except just to kind of understand the concept behind it. So we want to figure out the probability of a randomly selected day from this data being less than 70 degrees. So it works the same as a dot plot. I mean, it's just a different quantitative display. So less than 70 degrees, we've got that many data points. We just need to figure out how many total data points there are. I believe the total, if you guys haven't gone through and added it up for yourself, I believe it's 153, and someone can confirm that if they'd like. But assuming this was a problem on a test, you would need to go through and calculate it, make sure you got the correct number of total data points. And now it's just that this collection of data, 8, 10, and 15, so it'd be 33 out of 153. Nothing super fancy. I did want to mention that this is similar to stuff that you did before when we were looking at histograms and normal distributions. This is roughly normal, maybe slightly skewed, but it's approximately normal. And this is similar to just a manual calculation of what we would have done for normal CDF, right? So we would have said, okay, our lower bound is here, our upper bound is right here. What is the area under the curve for that? So it's similar. When you are doing a normal CDF calculation, it can also be considered that you're finding the probability
of getting in that range. So that is something that we'll come back to, that concept, but you can see how that applies for this empirical data. All right. So again, not going to go super in depth here. There's 153 measurements, and we've got between 75 and 85, looks like 67. And we could convert this into decimals if this is a multiple choice question. Maybe the answer choices are all in decimal. So we would get those numbers, we'd plug it in, we'd get our answer. Okay. The only other thing to mention about these types of problems is sometimes this is given not in absolute values, but in relative frequency. So I'm not going to go through all of them, but like maybe this is given as 0.052, and the next one, and I'm actually getting the real values here, this is 0.065 for this bin right here. So they might give you the relative frequencies of all of these bins rather than the absolute count. And that doesn't make it any more difficult or anything. You could just add up your relative frequencies to get your probability. Okay. So I don't want to spend a long time on that because it's really not the most complicated thing we're going to talk about today. Okay. Now there's not a whole lot to this slide. Basically, drawing pictures is one way to help make kind of understanding about the problem. So here is a problem, and we're going to draw a picture to make sense of it. So we've got a box of 134 greeting cards. 57 of them are sympathy cards. 60 of them featured animals. If 20 of them weren't sympathy cards and didn't feature animals, are sympathy cards and cards featuring animals mutually exclusive? So mutually exclusive, let's remember, well, let's actually visualize what mutually exclusive means, because we're going to draw with a Venn diagram. Mutually exclusive means both events can't happen at the same time. So in a Venn diagram, two mutually exclusive events would look like this. There's no overlap. Event A cannot coincide with event B in any way, shape, or form. So there's a Venn diagram of mutually exclusive events, and maybe that's a visual that you can keep in mind if you're trying to remember what is mutually exclusive. Oh yeah, separated Venn diagrams. So we want to figure out, are sympathy cards and cards featuring animals mutually exclusive? So that's kind of just a quick example. So let's actually draw this in context. I've got a box, a figurative box right here of 134 cards. I know that I have a group of cards here that are sympathy cards. I'll just put S for sympathy, and there's 57 of them. I've got another group of cards right here, which are animal. Let's put A for animal, and there are 60 of those. The only other information I have is that 20 cards weren't sympathy cards and didn't feature animals. So they don't fit in either of these groups. It's going to fit out here in the void on the outside of these groups. So 20 of them sit out here. And if these are mutually exclusive, the way we'll know it is because all these numbers, because there's no overlap between sympathy cards and animal, these numbers should all add up to 134. So 57, 60, and 20 should be able to be added together and equal the number of cards in the box. So if I do that, 57 plus 60 plus 20 gets me 137. Now I can't have 137 cards in the box because there's only 134. So that means some of my sympathy cards must feature animals. And how many?
Three.
3. Yeah, and this is something we're going to get to in chapter 15 starting tomorrow, the general addition rule. But I mean, it suffices to say right now that they're not mutually exclusive because there are going to be, so if I stretch this out a little bit, there's going to be a little bit of overlap between those two groups. So therefore, no, they're not. Okay, but drawing a picture can kind of help because otherwise this particular problem would be one, it's tough to keep all these ideas in your head straight. So Venn diagrams are very helpful, and I'll try and use that a little more. Okay, So these, for the rest of class, we're just going to be looking at some probability practice. These are actual questions from your textbook, you can tell. And I'm going to go through a number of these and kind of try and hit all the kind of more difficult nuances when you're dealing with probability, because some of it's pretty straightforward. Some of it gets kind of difficult. Okay, so let's talk about this. Sample spaces. Remember, sample spaces are the is basically the set of all possible outcomes for an event. Okay, so we're going to look at this event and we're going to look at what kind of outcomes are listed. And then the other part is, let's figure out if these events are equally likely. So we can roll 2 dice. That's the event. The outcome we're going to be recording is the sum of the numbers. So what's my sample space for this event?
Rolling a dice.
And that is the event. The sample space, remember, is all possible outcomes. So what are the outcomes we could get from the sum of the numbers on 2 dice?
1 to 12.
1 to 12?
Yeah. Or wait, 2 to 12. Sorry.
There you go. So 2 to 12. So you can get 2, 3, 4, ... all the way up to 12. So that's the first part of the question. And the second part is, are all of these events equally likely? If you watch the videos like you're supposed to, you'll already know the answer right off. Are these equally likely to happen?
No.
Okay, what's the most likely outcome?
Rolling a 7.
And does anyone remember the odds of rolling a 7 when you roll 2 dice?
Is it like 9/36?
So there's 36 possible rolls, and 6 of them are 7, so you end up with a 1 in 6 probability. So that's the highest probability you have for any outcome, 1 in 6. All right, so these are not equally distributed, and you end up with, it looks like a normal distribution. It's what we call a binomial distribution. Anyways, that is what we've got here. All right, a family has 3 children. Record each child's sex in order of birth. This one's a little bit weird to think through, but can anyone think of a possible outcome for this? And let's think through it just step by step. What is a possible outcome for the firstborn? Or if you have the full answer, you can say that.
50-50.
Yeah.
Go ahead.
50-50.
50-50 for, well, that's not going to be an outcome. Our actual outcome is going to be sex and order of birth. So the firstborn could be male or female. So let's just start off and say the firstborn was female. The secondborn could be male or female. Let's just say it was also a female. And the thirdborn could be male or female. And let's say the thirdborn was a female. I'm starting off with female, female, female on purpose. That way we can kind of methodically go through it. So that's one possible outcome. We have 3 kids and all 3 of them are females in order. And then we could have an outcome where we start off with 2 females and then we end up with a male for the 3rd child. Maybe we have a female first, then a male, then a female. And then a female, a male, and then a male. You can see what's happening. This is actually just powers of 2 that's going on. Every time we add another kid, we grow by a power of 2. So now we've got the possibility that we had a male and then a female and a female.
male, then female, then male, male, then male, then female, male, male, male. So essentially we expanded it out this way. Every single birth, there's 2 possible outcomes, male, female, and we just cubed it because there's 3 kids. So if we had added another kid, we would have had 16 possible outcomes. So luckily, in this example, we stopped at 3 kids. Okay, so are all of these outcomes equally likely?
I think so.
They are. Yeah. So yeah, it's equally likely. Each particular trial, there's each particular event has the same outcome no matter which one we're looking at. So there we go. That one's a little bit tricky just because of what they're asking. It's hard to know exactly what the outcomes look like, but hopefully it's clear in retrospect. Okay, toss 4 coins, record the number of tails. What's our sample space for this?
Heads or tails?
That's a result of an event, but our event of a single
0 to 4.
0 to 4, there you go. It's the number of tails. So we could get 0 tails, 1, 2, 3, or 4. Are all these equally likely?
Yes.
Okay. And this one's tricky, and we are going to come back to this concept when we get to binomial distributions later. But there's only one way to get 0 tails, and that means we have to get heads 4 times in a row. Heads, 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 heads. But we could get 2 tails lots of ways. We could, in 4 coin flips, we could do tails, tails, and then heads, heads. We could do tails and then get 2 heads in a row, and then another tails. We could do tails, heads, and I'm not going to list all of them, but there's lots of possible ways that we could get 2 coin flips. It turns out this is another distribution that looks normal. So they're not equally likely, and 2 is the most common outcome. But that's okay. I mean, it's just conceptually think through it. I don't think you're going to have a question like this, but it's good just to get your brain moving. Okay, and the last one. Toss a coin 10 times. Record the length of the longest run of heads.
One to 10.
Okay. Well, it definitely goes up to 10, but we
0
could,
to 10.
yeah, we could theoretically have 0 heads. And this is an example of, again, just some previews of stuff to come. This would be maybe modeled with what we call a geometric distribution. And we will get into all that fun stuff. That's chapter 17 and 18. So that's not going to be on your test. But there you go. This is the sample space. You're getting the idea with that. Okay. These are not equally likely. Let's just wrap it up. Certainly getting 10 in a row is very unusual. Getting 0 is very unusual. So somewhere in the middle is going to be the most likely. Okay. So let's go ahead. What am I doing? All right, some of these we're just going to talk through. So actually, let's just do this one right here. Commercial airplanes have an excellent safety record. Nevertheless, there are crashes occasionally with the loss of many lives. In the weeks following a crash, airlines often report a drop in the number of passengers, probably because people are afraid to risk flying. So here are a couple of thoughts. And a travel agent suggested that since the law of averages makes it highly unlikely to have 2 plane crashes within a few weeks of each other, flying soon after a crash is the safest time. What do you think?
It's probably just as likely.
All right. So yeah, we have, and the key thing I think keep in mind is that law of large numbers, right? Short-term trends are unpredictable. In the long term, you know, we might say, oh, only 1 in 1,000 flights, or whatever the statistic is, 1 in every 100,000 flights crashes. Long-term trends we can kind of calculate, but in the short term, anything's possible. You could have 2 flights crash back to back. So yeah, no, not good statistical reasoning right here. Now the airline proudly announces that it has set a new record for the longest period of safe flights. Are they due to have a crash?
Don't know.
Yeah, it's, again, the past can't predict the future, and every new trial, every new plane flight is its own possibility. So it doesn't depend on what happened the flight before it, generally speaking. So there you go. It's neither one of these are good statistical reasoning going on. All right. So this is something that we didn't talk about yesterday, but it's a pretty straightforward idea. If you are looking at the distribution of probabilities in your sample space, there are a couple of rules that have to be followed. First of all of the probabilities have to add up to 1. We did talk about that yesterday, but we didn't look at any examples. So here we go. If we look through all 5 of these distributions, so in this case, people could win 10, 20, 30, or 50% off on their groceries. And if we look in the first one, there's a 20% chance of each of those discounts, but that only adds up to 0.0 or to 0.8. So that is not a legitimate distribution because it has to add up to 1. So A is no good. B, we've got 50, 30, 20, 10. If you add that up, you get 1.1. So that's no good. If you add up the next one, 80 plus 10 plus 0.05, 0.05, that adds up to 1. We're good. The next one is 75, 0.25, 0.25, negative 0.25. That adds up to 1. So far, we're good. And then the next one adds up to 1. So the other criterion that has to be met is that every probability must be between 0 and 1. It's always a positive probability. So that, therefore, this is not a legitimate probability. So that means that this is not a legitimate probability distribution for the sample space. The C and E are both valid. Sure, you have a bunch of 0% probabilities, but it doesn't matter. We just know that you're guaranteed to get 10% off. Okay, so hopefully that's not a difficult concept. Okay, so we've got a few things going on. Remember, before we get into this too far, the addition rule says that if 2 events are mutually exclusive, we can add the probabilities together and you get the probability of either of them happening. The multiplication rule says that if 2 events are independent, then you can multiply the probabilities together and you will get the probability that both of them happen. Okay, and that's kind of the shorthand for both of those. We're going to be using those with all of our calculations today. So in this case, so funding comes from taxes based on assessed values. People's homes are assessed higher if they have extra features such as garages and swimming pools. So for a certain school district, 37% of homes have garages, 3% have swimming pools. The addition rule might suggest then that 40% of residences have a garage or a pool. And what's wrong with that reasoning?
Is it because it assumes they're mutually exclusive?
Yeah, it's assuming that they're mutually exclusive. But is it possible, or is it even likely, that you could have a pool and a garage?
Yes.
Yeah, so if that is the case, if these two, and remember, just think of mutually exclusive as these two, never the twain shall meet, right? So these two cannot mix if they're mutually exclusive, but I think it's fair to say, oh yeah, there's gonna be plenty of homes that have a pool that also have a garage. Okay, so those will overlap. They're not mutually exclusive. This calculation is no good. Okay. Next one. So we've got studies suggesting that 14% of people are left-handed. So since 0.14 times 0.14 is 0.0196, the multiplication rule might suggest that there's about a 2% chance that a brother and sister are both lefties. And what's wrong with that reasoning? And let me ask it this way. What is the criterion that must be met to use the multiplication rule?
They need to be independent, right?
Yep. This one's a little more subtle, but is it a good assumption or not that siblings are, whether they're right or left-handed, are independent of each other?
No, because maybe like genetics would do something.
Yeah, I'm thinking, I think that's basically right. You got it. So I would guess, I don't know the numbers, but I would guess across the population, there's a 14% chance of being left-handed. But if your older sibling is left-handed and then you're born, your probability might change based on that, and you might have a higher probability of being left-handed. So therefore, they're not independent. So 2% is not a good calculation. Okay, questions on these? And as we go through, and sorry if you had a question, I just interrupted over you, but as we're going through, if there's like a question that you don't know right now, you just want to look at it again, go ahead, like mark it on a piece of paper, say, oh, number 16, I want to go back to that one. And then you can stick around later if you want to go back to it, because you just want to talk through it again. Okay, but are there any questions here?
So if that problem were on a test, how would you answer that, like, formally?
If it was like an FRQ, I would say this calculation assumes, calculation assumes that siblings being right-handed or left-handed are independent, but this is a faulty assumption. This is a faulty assumption because, you know, genetics might play a role in your handedness.
Thanks.
Okay, are we getting to some of the fun ones? Well, I feel like we could skip this one. We'll just talk about it very briefly. So Jorge has applied to 3 colleges. Harvard accepts 9%, Stanford 10%, Penn accepts 16% of their applicants. He thinks he has a 35% chance of being admitted. And of course, how did he arrive at this? Well, he just added these together. And the assumption is that these are mutually exclusive. So, and that the fault there is, of course, some of the same people applied to 2 or all 3 of these. And some of the same people were admitted to all three. So if we were making a picture of this, we don't have Harvard, Stanford, and Penn applicants and acceptance. What we have is an overlap. We have Harvard, Penn, Stanford, and these overlap. They're not mutually exclusive, and therefore we can't just add those three together. All right. Okay, these are some fun ones. And then there's some other ones. Well, anyways, so let's see, I skipped over one, sorry. So right here, we've got a large introductory statistics lecture hall. The professor reports that 55% of the students enrolled have never taken a calculus course. 32% have taken only one semester, and the rest have taken 2 or more semesters of calculus. So you're randomly assigned to a group of 3 for a project. What's the probability that the first group you meet has studied 2 or more semesters of calculus? So maybe the first thing to do if we draw a picture for this is to kind of think about, are these mutually exclusive groups? We're about to be using some addition rule, and we want to make sure that this is the assumption has been met. I think it's fair to say you couldn't have simultaneously never taken a calculus course and have taken 1 semester of calculus. You couldn't have done 1 and 2 or more. So anyways, I think, yeah, we could have 0, 1, and 2 plus. These are independent, or not independent, sorry, mutually exclusive groups. So we've met that assumption. So what's the probability that the first group you meet has studied calculus? 2 or more semesters, that is. So the probability of 2 plus, well, I don't know that, but I know what 0 and 1 is, and these have to be, this is the entire sample space. 0, 1, and 2 plus is the entire sample space. So if I just subtract 55 and 32% from 100%, I'll get my answer. You can show the math. 100 or 1.00 minus 0.55 minus 0.32. I'm not going to get as fancy with the probability notation on this one because we get, what is that, 17 or 13. 0.13. Okay, so there's a 0.13 probability that someone has done 2 plus semesters. Some calculus. Okay, well, some calculus isn't specific, but I know it's not none. So basically, I just want to get the probability that, how about the probability that it's not 0? So really a way of saying that is the complement of 0. I don't care if it's 1, 2, or more than that. So the complement of 0 is going to be 1 minus the probability of 0. I know the probability of 0 is 0.55, so 1 minus 0.55 gives me 0.45. There it is. And no more than 1 semester of calculus. So the only condition I'm not interested in are the people that have taken 2 or more semesters of calculus. So in this case, I can say the probability of 2 plus complement. I don't want that. I want everything besides that probability. So now I can do 1 minus the probability of 2 plus. And I know it's 0.13, so it's going to be 1 minus 0.13, which gives me 0.87. Okay, so addition rule really works pretty straightforward. There was a little bit of difficulty with kind of recognizing, are we using this regular or a complement rule for this? But are there questions on how we approach this or what to do? Okay, and I'm going to write down real quick because we're going to use these same numbers. So the probability of 0 is 0.55. The probability of 1 is 0.32, and the probability of 2 plus is 0.13. So I should have cleared all this stuff before, but whatever, I'll get rid of it. This is where it gets a little bit more interesting, and I'm going to try and be very careful how I talk about this because it can get very difficult. When we use our multiplication rule, okay, so we are going to be looking at the probability of two of our group mates, our other two group mates, the probability that they meet certain criteria. So the first one, neither has studied calculus. So the probability that both of them, just think about what you're saying, and maybe I'll write it out this way. So for A, I'm saying the probability of 0 and 0. And what I mean by that is the probability that the first group mate has 0 semesters of calculus, and the probability of the second group mate has 0 as well. So just my actual language, the probability of one having 0 and the other having 0, that and tells me I'm using my multiplication rule. So that's going to be just the probability of, if these are independent, and we're going to make that assumption for now, the probability of 0 times the probability of 0. Because there's event A right here, there's event B, and I'm just going to multiply the probability of each of those together. All right. So probability of 0 is 0.55 times 0.55, which gives 0.3025. I have just over a 30% chance of getting two group mates who have neither of them have studied calculus. Okay, so let's look at the next one. Both have studied at least one semester of calculus. So maybe the way I can think about this one is the probability that they haven't studied 0. I don't care if it's 1, 2, or more. So the probability that they haven't studied 0 and the probability that they haven't studied 0. All right, which is the same as something like that. So anyways, if I do that, I'm just going to take the probability of 0 complement and multiply it times the probability of 0 complement. So what's the complement of 0? That's going to be just 1 minus the probability of 0. And I know I'm going through every single step, and you might not need to see it, but it's not going to hurt you to see it. So 1 minus 0.55. So there's a 45% chance that they've done some calculus. So now we get 0.45 times 0.45, which gets me 0.2025. Okay. So the last one is the one that's going to give us the most fits. It doesn't seem like it's any more difficult than the others, but there's something else going on here. The probability that at least one has had more than one semester of calculus. And let's kind of first of all see the difference between that question and the first two. In the first one, we're saying that neither has studied calculus. So if I just think about this as how many have studied calculus here? 0. In this case, how many have studied, in the second problem, how many have studied calculus? Both of them, 2. There's only one scenario that I'm investigating. Either neither of them have studied calculus or both of them have studied calculus. The last one says at least one has had more than one semester of calculus. So how many situations meet this criteria? Well, if one of them has studied calculus, that's fine. If 2 of them have studied calculus, that's fine. The only thing that doesn't work is if 0 has studied. So now I have 2 success conditions and maybe different ways of getting there. You know, if this makes sense, if only one of them is taking calculus, it doesn't matter if it's the first or the second class group mate. So I have 3 possible outcomes that lead to this. All right, so this is why it's a little bit more confusing just on that conceptual side. So I want to approach this in a different way. So I'm going to pause right here. Is this difference making sense for you guys? Okay, so it's kind of making sense. We're going to see more problems like this. So hopefully it's going to, through exposure, just sink in a little bit. Let me show you how we're going to approach this. I'm going to clear everything off my page. All right, at least one has had more than 1 semester of calculus. I want to think about this the other way. What is the opposite of this? The opposite of at least one having studied at least 1 semester of college, or sorry, more than 1 semester of college. The opposite of that is that both of them have had 1 or less. So the opposite, the inverse, or whatever we want to say here, the opposite is that both have studied 0 or 1 semesters. Okay. And if I can find that probability, then I can just do the complement of that. So I'm going to do the probability that both have taken 0 or 1 semesters, complement, and that equals the probability that at least one of them has taken more than 1 semester. Okay. Again, we're going to look at more examples like this. That's why I told you this last one is the real mind bender. Okay, so now I want to kind of see how we can figure this out. The complement of both of them having taken 0 or 1 semesters. So that's going to be the probability that the first guy only has done 0 or 1, gal or lady, or a guy or lady. And the second one has only done 0 or 1, and the complement of that. So what's the probability that 0 or 1 semesters were taken? Well, it's just going to be the probability of 0, which was 0.55, and the probability of 1, which was 0.32. It's those 2 added together. So the probability that someone has done 0 or 1 semesters is going to be 0.87 and 0.87. And of course, the complement of this in the end. So what this does is I can do my 0.87 times itself. Which gives me 0.7569 complement. And what this is saying is, I want to make sure this number is clear what that means. There's a 75.69% chance that both of my group mates have taken 0 or 1 semesters of calculus. So if that is not true, then that means at least one of them has taken more than 1 semester of calculus. So I'm going to do 1 minus 0.7569. All right. And that gets me 0.2431. There it is. 24% chance that at least one group mate has had more than 1 semester of calculus. Easy, right? All right, we will look at another. You can see why I definitely wanted to go through these types of problems as a class. Hopefully we can build up some fluency with it. We're gonna take just very little time with this. This is related to problem number 22. we use the multiplication rule. Remember, for the multiplication rule to be valid, these have to be independent, and the probability of event B can't be affected by what happens with event A. Now, it's not reasonable to use this assumption because in a small class, let's say there's only 30 kids in the class, if we go through and assign the first one to every group, well, we've already used up, 10 of the 30 kids, so the probability of who's going to end up in your group next is not the same. We have a different pool to pick from. So it's not fair to use this assumption, but for our purposes, we'll make it work. Okay. And we would just say something to that effect. Okay. I want to skip this one. Let's see. I want to skip this one too because it's not as difficult of a problem. If you guys have questions on this, on any of these, you can just contact me, let me know. This is one I do want to go over. We don't need to really write anything. We can just think about it. So we're looking at various blood types, and we have the idea of disjoint or mutually exclusive events and independent events. So we don't need to know what happened in exercise 32, but the question here, if you examine one person, are the events that the person is type A and that the person is type B disjoint, independent, or neither?
Does having like a blood type AB count as, would that count for something?
It's a good question. I think, and I didn't ever look at an answer key here, I think AB is a distinct blood type from A and B, so I don't think they're interchangeable.
Okay. So in that case, it would be independent, right? Because you can have both.
Well, you can't have both. That doesn't mean they're independent. It means they're,
Oh, sorry, mutually exclusive.
there you go.
That's what I meant.
Disjoint, mutually exclusive. Yeah. So there you go. That is the answer here. I'm assuming, again, I'm not looking at the answer key, but I think it's a safe assumption. If you examine two people, are the events that the first is type A and the second type B disjoint, independent, or neither?
They're independent.
There you go. They are independent. It's fair to say across an entire population, sampling one person from the population isn't going to really change the probabilities for the second person. So yeah, if the result, the outcome for the first person doesn't change the second, they're independent. Okay. The last one is really the reason I wanted to look at this question. Can disjoint events ever be independent? What do you guys think?
I think no, because if one happens, the other one automatically can't happen, so they are dependent on one another.
Perfect. That's a really succinct, good explanation. I'm going to change pages. We're going to talk about that still. Don't worry about this problem just yet. We're going to get to that. I just wanted to have some space to write. But that's exactly, there's two ways of looking at it, and we're going to look at it conceptually like Sam just said. If these are mutually exclusive, A and B, and A happens, then of course we just changed the probability of B happening. That probability went down to 0. So if A and B in this case were flipping heads or tails, then as soon as heads lands, then tails probability goes down to 0. So they are not independent. They are mutually exclusive, not independent. So that's just a conceptual way of thinking about it. But a mathematical way of thinking about it, we know that for independence, the probability of A and B equals the probability of A times the probability of B. Now, we can think about mutually exclusive this way. You can say A or B equals probability of A plus the probability of B. That's one way, but more to the point, two events are mutually exclusive if the probability of A and B equals 0. So, if we just do a little bit of algebraic substitution right here, there is one case where you can have a probability, where two events can be mutually exclusive and independent, but that's only whenever one or both of the probabilities is 0. So if I'm trying to think of a good example. Maybe if your event A was flipping a coin and getting a heads or a tails. So the probability of heads or tails. And this one right here is the probability of getting, sorry, what's going on? Of getting heads, not heads, and not tails. Now we know the probability of getting not heads and not tails. Okay, sorry, that just went away. The probability of getting not heads and not tails is 0. We're gonna have to get one or the other. But to be fair, those are mutually exclusive and they are independent. One of them happening doesn't change the probability of another, but this is what we call a trivial case where it's only when one of the probabilities is 0. So just to simplify all this down, practically speaking, events can't be mutually exclusive and independent. Again, I'm not sure if that was helpful or if that was just confusing, but hopefully it was helpful. All right, let's get to this where we got some stuff going on. I don't want to go through all of these because some of them are pretty straightforward. So I'll just set up the problem for this one. So we've got a slot machine with 3 independently spinning wheels. We know they're independent, so we don't need to worry about that assumption. Each has 10 equally likely symbols. You can see the breakdown of that. If you play, what's the probability that you get 3 lemons? So we want the probability of lemon and lemon and lemon. Since they're all independent, we just need to multiply the probability of a lemon 3 times. No fruit means the probability of no fruit, so I'll just put fruit complement, which means no fruit, and the complement of fruit, which means, again, no fruit, and complement of fruit. So maybe if we look at that one a little bit more in depth, lemons and cherries are our fruits. So if there's 5 out of 10, the complement of that is also going to be 5 out of 10. If I'm going too fast through this, I'm trying to get to the harder problems. So basically, this is the probability of 0.5 and 0.5 and 0.5. We just multiply those 3 together, and we get our final probability. Okay. Let's look at D and E. So in C, it's what's the probability of getting 3 bells. So that one's pretty straightforward. We can find the probability of a bell. To get no bells means we want the complement of that. So a bell complement and bell complement and bell complement. All right, so the complement of getting a bell is, well, if there's 1 bell out of 10, then the probability of bell complement is going to be 1 minus 1/10, which is 9/10, or 0.9. So we just want to do 0.9 times 0.9 times 0.9, which when you multiply that out should give you 0.729. %73% probability of getting no bells. All right, so again, those first four, fairly straightforward. And this is the other really kind of confusing type at the end. So let's kind of think through these first four scenarios. 3 lemons, there's only one case where we get 3 lemons, and that's if we get lemon, lemon, lemon. There's only one case where we get no fruit, which is fruit complement, fruit complement, fruit complement. Then you get 3 bells, so bell, 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 and then no bells, so bell complement, bell complement, bell complement. This is the only outcome that gives us the success condition. But when we get to the last one, at least 1 bar. I have a lot of possibilities here. So I'll use B for bar, I'll use BA. So I could get a bar first with, it doesn't matter what I get here, just something and something. I could get a bar here, and I could get a bar here and get something here. And there's 6 possible ways of getting this. 7, I think, actually, whatever. So all of these are possible outcomes, and we could just keep coming up with different ways of having this happen. So 7 possible ways of getting this. So it's not as straightforward as let me calculate the possibility of this one outcome. Now I want to see what is the only way that I fail to get this. What is the only way that I fail in meeting that criterion? The only way I fail is if I don't get a bar, don't get a bar, don't get a bar. So rather than worry about all these, I'm going to worry about the complement of my failure. Right. Again, I'm going to pause right there. Conceptually, does that make sense? Okay. So it's whenever you see this at least one that you need to kind of read through that again and say, oh, this is going to be one of those weird ones where I want to find the complement of failing. So if I get no bars and I get the complement of that, I'm done. All right, so now knowing that, that's the hard part of this problem. Now I just need to think, okay, great. So what's the probability of no bars, not getting a bar, and not getting a bar, and not getting a bar, and then the complement of all that. Okay, so let's see. The probability of not getting a bar, there are 4 bars. I won't do the math by hand. We know it's going to be 0.6. There's 6 out of 10 possible ways to not get bars. So that's going to be the same, 0.6, 0.6, 0.6. And I want the complement of that. So now I can just do those 3 multiplied together. So it's going to be really 1 minus 0.6 times 0.6 times 0.6. And that's my final answer. So you guys can do that. Okay, there it is. Almost an 80% chance of getting at least one bar. And just to repeat myself, it doesn't matter if we get 1, 2, or 3, where that bar shows up, where 2 of the bars show up, it doesn't matter. There's a 78% chance that we're going to get at least one somewhere. So there you go. So is that making a little bit more sense now? Okay. I know it's not immediately one of these things that you'll pick up. No one picks this up right away. It takes a little bit of thinking through and internalizing that idea. All right, I was only going to do one more of these. I did problem 40. Let me see if I want to do the same problem. Why not? Just because, you guys can figure these out. So all of these are basically the same thing going on. So we'll just look at problem 40 real quick. And I'll go through it a little faster now that hopefully you're feeling pretty confident with it. Census reports for a city indicate that 62% of residents classify themselves as Christian, 12% as Jewish, 16% as members of other religions. The remaining residents classify themselves as non-religious. Polling organizations seeking information about public opinions want to be sure to talk with people holding a variety of religious views and make random phone calls. Among the 4 people they call, what is the probability that they reach? All Christians, no Jews, at least one person who is non-religious. All right, and before we do this, we'll just look at the probability that it's Christian is going to be 0.62. Probability that they're Jewish is 0.12. Probability of other is 0.16. We can quickly calculate the probability of non-religious, doing 1 minus all of that, which is 0.1. Let's put 0.10. So there we go. That is a legitimate probability distribution because each one of them are between 0 and 1, and it adds up to 100%. Okay. So the probability that they're all Christians. Straightforward. The only way we succeed at this is if it's Christian, 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 Christian. We're talking to 4 people. So this is basically just the probability of Christian and Christian and Christian and Christian. And when we do that, that's going to be 0.62 times 0.62 times 0.62 times 0.62. And of course, you just do 0.62 to the 4th power. And in this very simple calculation, it's about 14.8%. It's multiple choice, just see what the answer choice is given in, and you'll respond that way. 14.8%. No Jews. So we had to see the probability that someone is not Jewish. It's probability of not Jewish, and not Jewish, and not Jewish, and not Jewish. So the key thing to look out for here is like the all or nothing. If it's all or nothing, you can approach it in a pretty straightforward way. If it's the at least one, that's where it gets more complicated. Okay, so not being Jewish is going to be 1 minus 0.12, so 0.88. And I'll just do that to the 4th power. And there it is. I got this probability. All right. So the last little bit right here, at least one person who is non-religious. So the failure condition is going to be every person is religious. So I want to get the complement. I'll just write it over here. So the probability of religious, I'll use R for religious, and religious, and religious, and religious complement. Because the complement of that will be the probability that at least one person is non-religious. Okay, so there we go. That's just going to be 1 minus the probability of religious and religious and religious and religious. So 1 minus point. Now the religious probability is this combined up here. That's 0.9 to the 4th power. So once you get the hang of it, it doesn't take a long time to do the calculation. It just takes a little bit the first few times. And I got 0.3439. Okay. So I know this was a longer class, but I just wanted to spend the day going through a lot of types of problems. Hopefully you feel more confident with all these types of things. Your homework is going to be really duplicates of what we did in class today. So hopefully you can use this video or just what you learned today and get through these problems no issue. Tomorrow we're going to start chapter 15. And if you have any questions, you can stick around. But other than that, have a wonderful day and I will see you tomorrow.